Distribution. Measures of dispersion describe how varied or dispersed a dataset is. They include range, interquartile range, variance, and standard deviation. Range. The simplest measure of dispersion is the range, which is the difference between the maximum value and the minimum value in a dataset. The range is simple to calculate, but it has limitations. Certainly a range of 150 indicates more dispersion than a range of 10, but without looking more closely at the data we cannot know if the comparatively wide range of 150 is truly indicative of how spread out all of the data points are, or whether the range is being affected by one or more outliers. We can improve on the range by using measures that take into account not just the minimum and maximum values, but rather every value in the dataset. Page 145. The range has a further limitation when it is used with sample data. Specifically, it can be a poor predictor of the dispersion of data for the entire population. Two observations in a sample, even if they are the minimum and maximum values, might not necessarily reflect the population as a whole. Interquartile range. Another way to analyze the shape of a data set is to use the interquartile range, which focuses on the median. Taking the term apart a bit can help us better understand it. A quartile is one of four groups into which the data in a data set are grouped, with each quartile representing 25%, or 1/4, of the observations. To create quartiles, we place the data in order from the lowest value to the highest value, just as we do when we want to find the median or range. The cutoff value for each quartile is a percentile, a value on a scale of 100 that indicates the percent of a distribution that is equal to or below it. Then we group the values as follows. Quartile 1, the lowest 25% of observations, representing all data points from the minimum value through the 25th percentile. Quartile 2, the next 25% of observations. Its cutoff is the median, representing all data points between the 25th percentile and the 50th percentile. Quartile 3 begins at the median and extends to the third 25% of observations, representing all data points between the 50th percentile and the 75th percentile. Quartile 4, the highest 25% of observations, representing all data points from the 75th percentile to the maximum value. Excel or Tableau ranks the observations automatically when calculating quartiles. The prefix inter in the word interquartile implies that we are not interested in all four quartiles but rather the middle section, specifically quartile 2 and quartile 3. The interquartile range is thus the range of data that surrounds the median. When you are analyzing a sample instead of a population, the interquartile range is considered more helpful than the range as a measure of dispersion because it focuses on the most common values and minimizes the risk of outliers too heavily influencing the range. Variance and standard deviation. More sophisticated measures to describe the dispersion of your data in relation to the mean values are variance and standard deviation. The variance is calculated by taking the average of the square deviations from the mean for each observation, and the standard deviation is the square root of the variance. The standard deviation is expressed in the same unit as the data values, which makes it easier to interpret. Variance is expressed in squared values, which makes it more challenging to interpret. It's true that these terms feel very technical. Fortunately, tools such as Excel, Tableau, and Power BI help us find the variance and standard deviation without having to perform the calculations manually. When comparing two data sets, the data set with a larger standard deviation has more variation, or dispersion, in the data around its mean. For example, financial analysts often measure the volatility of a stock price using standard deviation as a measure of risk. The greater the standard deviation, and thus, the greater dispersion around its mean, the riskier the stock is considered. The calculations for standard deviation and for variance differ based on whether the data set consists of a sample or a population. Because we can never be 100% confident that our samples perfectly reflect the parameters of a population, the calculations for standard deviation for a sample differ from those for a population to minimize non-response bias and selection bias. Page 146. Continuous probability distributions. Now that we understand measures of central tendency and dispersion, let's look at some continuous data distributions that are frequently used. Normal distribution. The normal, Gaussian, distribution is a bell-shaped probability distribution that is symmetric about its mean, with the data points closer to its mean more frequent than the data points further from its mean. As Exhibit 3.7 shows, observations within one standard deviation of the mean include 68% of the data points. Observations within two standard deviations of the mean include 95% of the data points, and observations within three standard deviations of the mean include 99.7% of the data points. The normal distribution has a kurtosis of 3, so in combination with the skewness, normal distribution has a skew level of 0, and parenthesis. The two values can help you determine how well your data distribution approximates the normal distribution. Many of the statistical tests that we use in data analytics are based on the normal distribution and how many standard deviations a sample observation is from its mean. Many naturally occurring continuous distributions conform to the normal distribution, including newborn weight, population height, population IQ, shoe size, and employee performance. The standard normal distribution and z-scores. A special case of the normal distribution is the standard normal distribution, which has a mean, median, and mode of 0 and a standard deviation of 1. The standard normal distribution is a theoretical distribution. That is, it does not represent a real distribution. Instead, it is used as the basis for standardizing data across different distributions to make comparisons easier or to calculate probabilities of individual observations occurring in a population. In any distribution that we can assume to be normal, we can transform the observations into z-scores that represent standardized values. A z-score tells us how many standard deviations a data point, parenthesis, or observation, is from the mean. A z-score of, parenthesis, plus, and parenthesis, 1 means that page 147 the observation is 1 standard deviation above the mean. A z-score of -2 means that the observation is 2 standard deviations below the mean. For example, the mean IQ is 100 with a standard deviation of 15. Albert Einstein's IQ was reported to be 160, or 4 standard deviations above the mean, giving his IQ a z-score of 4 and suggesting a typically high intelligence. Many of the statistical tests employed in data analytics are based on the standard normal distribution and how many standard deviations a sample observation is from its mean. Uniform distribution. A uniform distribution of continuous data is recognizable by its rectangular shape. It is characterized by a range of values that are all equally likely to occur. For example, if all customers are equally likely to spend between 5 minutes and 45 minutes shopping in a store, data regarding customer time in the store will roughly follow a uniform distribution, similar to the one shown in Exhibit 3.8. Data analytics and your career. A deep knowledge of statistics continues to offer excellent career opportunities. According to the U.S. Bureau of Labor Statistics, BLS, 44,800 people were employed as mathematicians or statisticians in 2020, and this number is expected to grow 33% by 2030. This rate is much faster than the average for all occupations in the United States. In 2020, the median income for mathematicians or statisticians was $93,290. One understanding of data and statistics continues to be an important and growing area in the economy. Progress check. Why is it useful to understand the center of your data's distribution? Why is it helpful to understand how dispersed your data are? What does a data set with 0 skewness represent? What does a negative skewness represent? A positive skewness? When comparing data sets, what purpose does the standard deviation serve? If data set A has a higher standard deviation than data set B, what does that tell you? Page 148. 3.4 Using software tools to create summary statistics. LO 3.4. Use software tools to create summary statistics. In the previous section we introduced statistics that we will use throughout this book. At this point, it is helpful to learn how to calculate these statistics using Excel, Power BI, and Tableau. The chart in Exhibit 3.9 color codes each calculation as green, orange, or red. The green items are straightforward in the tool of choice. The orange items require a bit of a workaround, but learning those workarounds is very useful. The red items are not easily done in the chosen software package. Exhibit 3.9. Calculating selected summary statistics with Excel, Power BI, and Tableau. Table summary. A table has 4 columns and 8 rows. Column 1 lists measures. Column 2 titled Excel options, function, divided by formula, data analysis tool pack, parenthesis, DA, and parenthesis, and pivot table has 3 subcolumns titled equals, function, parenthesis, and parenthesis, or equals, formula, DA, and pivot table. Column 3 is titled Power BI. Column 4 titled Tableau options, visualization and summary card, parenthesis, SC, and parenthesis, has 2 subcolumns titled visualization and SC. Equals, included DAX, equals, data analysis expressions array, equals, a set of numbers, often used in the context of Excel functions to indicate that a calculation requires more than one single value. Excel functions. All Excel functions begin with an equal, parenthesis, equals, and parenthesis, sign, which is the signal to Excel to perform a calculation. Each set of parentheses should contain at least one argument. In Excel, an argument is a value that a function uses to perform calculations. With the exception of IQR, interquartile range, all of the Excel functions require that a range of cells be specified. Page 149 for IQR, a range of cells is specified followed by the quartile number. Exhibit 3.10 provides an example of using an Excel function to calculate the average sales price. Excel data analysis tool pack. Descriptive statistics. As noted in Chapter 2, Excel offers a data analysis tool pack that helps you perform many of the business analytics explained in this text. If you aren't sure if you've installed the Excel data analysis tool pack, look for it on the data is greater than analyze ribbon. Exhibit 3.11 and parenthesis. The appearance may vary by Mac, PC, and version of Excel. If you haven't installed the data analysis tool pack yet, do so now following the instructions in Appendix E. To generate descriptive statistics, select data is greater than analyze is greater than data analysis. A dialog box will open, as shown in Exhibit 3.12. Select descriptive statistics. Page 150. Descriptive statistics generates basic statistics, including the mean, average, median, mode, skewness, standard deviation, minimum, and maximum of a data set as shown in Exhibit 3.13 for the salaries of a fictitious 10-person company, tires minus are us. The median and the mode are the same at $34,000, but the mean, parenthesis, at $40,600, and parenthesis, is higher than the median and the mode because the maximum value of $100,000 skews the mean higher. The skewness is 3.16, indicating that the data are skewed to the right, or positively skewed. Recall that a perfectly symmetrical distribution has a skew value of 0. If the skew value is below 0, then the data set is skewed to the left, or negatively skewed. If the skew value is above 0, then the data set is skewed to the right, or positively skewed. Excel's kurtosis value is relative to the normal distribution. The closer the kurtosis is to 0, the closer the shape is to a normal distribution. We can also gain insight into our distribution based on whether kurtosis is negative or positive. A negative excess kurtosis suggests that the distribution is flatter, so the values in the tails are less extreme. A positive excess kurtosis, like the one in Exhibit 3.13, suggests a taller, or more peaked distribution, which implies that the values in the tails are more extreme. Kurtosis is particularly important when your analysis is related to risk management. Riskier distributions have positive kurtosis, whereas less risky distributions have negative kurtosis. Changing the default aggregation in Excel pivot table, Power BI, and Tableau. Excel pivot tables, Power BI, and Tableau visualizations all provide great tools to summarize data. They can aggregate data in a variety of ways, including SUM, average, count, maximum, minimum, and standard deviation. Exhibits 3.14, 3.15, and 3.16 show how to change the default aggregate measure easily in an Excel pivot table, Power BI visualization.